Good afternoon, and welcome to NASA headquarters. I'm Dwayne Brown with the Office of Communications. Today's briefing is about NASA's Lunar Atmosphere and Dust Environment Explorer, or LADEE, a robotic mission with launch about 2 weeks away, where the spacecraft will orbit the moon to help scientists answer prevailing questions about our moon. And this mission has many firsts, in which you will hear firsthand about today. Of course, for more details about the mission and updates on launch, please visit NASA's website at www.nasa.gov/LADEE and join the conversation on Twitter at @NASALADEE. And during our question and answer period, please, social media, join and bring in your questions for the scientists to answer at #AskNASA. And of course, the conversation is brewing and a lot is going on. Follow NASA and missions updates on social media, on Twitter, Facebook, and other sites. Before I introduce today's panelists today, to start us off with opening remarks, please welcome the Associate Administrator for NASA's Science Mission Directorate, John Grunsfeld.
Thank you, Dwayne. I love this mission. LADEE is going to be fantastic. I'm getting really excited as we move to the launch pad. First of all, because it's going to the moon. And ever since I was a young boy, like so many folks, looking up at the sky, I've wondered about the moon. With the Lunar Reconnaissance Orbiter, which is still in orbit around the moon, we've learned an enormous amount about the surface of the moon. With GRAIL, we've studied the interior of the moon. And now with LADEE, we're going to learn about the moon's atmosphere, which is something very mysterious and we know very little bit about. And so this is a particularly exciting mission for us. The other reason I love it is it launches from Wallops. And Dwayne was talking about the first, and you're going to hear a lot more about all of these things. These are just some personal things that I think are great. And another is that it has a laser comm demo. And this is something I'm a huge fan of. And finally, it's a modular spacecraft, so that while this is the lunar version, it's a type of architecture that we might be able to use in a lot of different types of science experiments and others. So I'm very excited. You'll hear a lot more about it. Please bring your questions, and on to the rest of the show.
Thank you, John. So let's get to our panelists. They will have brief presentations, but let me introduce them to you. First, Joan Salute, LADEE Program Executive, NASA Headquarters. Butler Hine, LADEE Project Manager from NASA's Ames Research Center, Moffett Field, California. Sarah Noble, LADEE Program Scientist, NASA Headquarters. Don Cornwell, Mission Manager for the Lunar Laser Communications Demonstration at NASA's Goddard Space Flight Center in Greenbelt, Maryland. And Doug Voss, the Launch Manager at Wallops. And with that, I'll toss it to you, Joan.
Thank you, Dwayne. Thank you for coming this afternoon to learn more about LADEE. LADEE is scheduled to launch Friday, September 6th, which is just 2 short weeks from tomorrow, from the eastern shore of Virginia at the Wallops Flight Facility. LADEE is sponsored by the Science Mission Directorate and will have 3 scientific instruments to measure the atmosphere and the dust, as John mentioned. In addition, it has what we call the tech demo, or tech demonstration, which is the Lunar Laser Optical Communications Demonstration. This tech demo is sponsored by the Human Exploration Operations Missions Directorate. Once in orbit, LADEE will orbit the moon in a lunar equatorial orbit to measure what the atmosphere is made up of and how that varies over time. It will also try to understand whether or not the dust is levitated from the surface, and this is one of the mysteries that you'll hear about in a minute. Before you hear the details of the mission from all of the fellow panelists, I'd like to try to put into perspective the mission development for this project. In 2008, we formulated a new program, the Lunar Quest program, which was designed specifically to accelerate lunar exploration, lunar scientific exploration. we wanted to do it before humans went back to the moon. At this time, the Science Mission Directorate was trying to figure out how to make spacecraft less expensive. And Ames had come up with what we're calling the reusable modular design. They thought they could do it less expensively than we've done it in the past. So the mission was directed to Ames with a low-cost commitment. Now, 5 years later, we're actually ready to go. 5 years after the program started, we're ready to go back to the moon. From the beginning, this has been a great partnership across NASA. We augmented the Ames team with Goddard, both Greenbelt and Wallops. Goddard has a wealth of expertise that was able to supplement the Ames team. The program office, we went to Marshall Space Flight Center, where we already had our Discovery and New Frontiers program office well established. During the years of development, we've added team members from Kennedy in Florida, Glenn in Ohio, JPL in California, Langley in Virginia, and Johnson Space Center in Texas. Where the team needed additional expertise, they reached out and got it from the other NASA centers. The mission was directed to Ames for overall project management, and they have designed, built, integrated, and tested the spacecraft. They'll be responsible for all of the mission operations during the mission. NASA Goddard Greenbelt was responsible for developing the payload, which included all 3 scientific instruments and the tech demo. And they'll be responsible to run the Science Operations Center during the mission. NASA Wallops has the privilege to launch us into space. They have all the launch vehicle services and the range operations. We have a reimbursable agreement with the Air Force to supply the launch vehicle, and they're responsible for the mission assurance of the launch vehicle. We're very proud to be breaking new ground in a number of areas. This includes the first time Ames has built a spacecraft in-house without the help of a prime contractor. It's the first deep space mission to be launched from Wallops, the first Minotaur 4 or 5 to be launched from Wallops, and it's the maiden voyage of the Minotaur 5 anywhere. And as was mentioned, it's NASA's first test from space of the optical communications we're especially excited about. So now I'd like to ask Butler, the project manager from Ames, to go over some mission highlights.
Thanks, Joan. One of the things that is a first is we're trying out a modular spacecraft bus that is not designed for a single mission. It's designed in a modular fashion so you can use it for different missions by combining it in different ways. If you bring up my first slide, you can see the architecture. You can see the individual modules. There's a top module which contains most of the electronics and power switching devices on the observatory. There's a payload module where the 2 biggest instruments are located on opposite sides for balance. It also has our reaction wheels for fine pointing control. There's an extension module, and within that is the propulsion module. You can put different types of propulsion modules in this spacecraft architecture, but in this case, we're using a proven commercial design from Space Systems Loral that is a biprop system, meaning it has 2 fuel tanks and 2 oxidizer tanks, and it's a pressurized system. Some things to notice about this spacecraft design is it does not have the wings that you normally see on a lot of modern designs. Those wings give you a lot of power. They're deployed after launch, but they require that you always point at the sun because it's very bad for a spacecraft to lose power, obviously. So you always want to be pointing at the sun. One of the characteristics of this design that you can see is that it has solar panels all over the spacecraft. What that means is the spacecraft can be in pretty much any attitude and still generate power. That means it's a very inherently safe design. It's very difficult for this spacecraft to ever get in a condition that it can't wake up from. If you go to the next slide, what you'll see is this is what LADEE looks like right now. When we put the spacecraft together in this modular fashion, it was done in a way to lower the cost of production. One of the characteristics is this carbon composite frame that the spacecraft is built of to be very strong and very lightweight. The other thing we did was take advantage of any modern electronics, any modern devices that were designed for space rather than designing things from scratch. So this is think of it as a bus that you can use for a multitude of purposes. I'm very happy that we got the chance to fly this on the first time for a lunar mission because that really proves out some of the characteristics of the bus. After we put the bus together, we went through a lot of testing. You really want a spacecraft to experience the rigors of space before you fly it. So we shook it, we blasted it with loud noises, we simulated the shock when it separates from the launch vehicle. We put it in a hard vacuum chamber, we baked it to high temperatures, cooled it to very low temperatures, tested all of its communications equipment with the actual relay satellites that we're going to be using. We did all this in preparation to shipping it to the range. It's been at the range this summer. We just finished doing all the spin balancing, all the fueling of the spacecraft. And now it's encapsulated with the fifth stage, the upper stage. It's encapsulated in the nose cone of the rocket. This weekend, we plan to roll it out and stack it on the rest of the launch vehicle, which is already stacked at the pad. If you go to the last animation, you can see what it looks like in flight. This is an animation showing what you would see if you were outside the spacecraft looking at it on the way to the moon. There's a couple of interesting things about how we get to the moon. If you're my generation, you remember the Apollo era. They got to the moon in a classic figure-8 pattern. It's a very efficient way of getting to the moon. It takes a lot of fuel, however. And because of trying to optimize the amount of fuel that we have for the science mission, we go in a different way. We launch from Wallops, and then we go into these elliptic orbits around the Earth. We take a couple of passes around the Earth, and each pass we get higher and higher until finally on the third pass, we're hanging out there in space right around where the moon's going to come by. It swings by, whips us around behind it, and then once we come out from behind the moon, we do a big braking burn with our main engine that you can see there. That braking burn is what captures us around the moon. We spend about 30 days commissioning the science instruments. We do the optical comm experiment during that time, and then we drop down into the low science orbit. The low science orbit is about 30 to 70 to 90 miles above the lunar surface. It's very low. And when you're that low above the moon, the lumpy gravity field requires a lot of fuel to maintain. So we drop down into that orbit, do our active science where we're flying in and out of the light-dark terminators around the moon. And then at the end of the mission, we terminate the mission by intentionally crashing into the lunar surface, taking science on the way down. And now I'd like Sarah to talk about the science aspects of the mission.
Thanks, Butler. So as you've heard, LADEE has two main science goals: to understand the lunar atmosphere as well as the dust environment around the moon. And I think sometimes people are a little taken aback when we start talking about the lunar atmosphere because, right, we were told in school that the moon doesn't have an atmosphere. It does, it's really, really thin. It's so thin that the individual molecules that make up the atmosphere are so few and far between that they don't interact with each other. They never collide. A collisionless environment, which is something we call an exosphere. If I can get my first graphic, the Earth actually has an exosphere as well, but you actually have to get out past where the International Space Station orbits before you get to this condition that we can consider an exosphere. On the moon, that actually happens right at the surface. So the term we use for this class of atmosphere is a surface boundary exosphere. And it's not just the moon. Surface boundary exospheres turn out to be the most common type of atmosphere we have in the solar system. So Mercury, a lot of the moons of other planets, even some large asteroids are big enough to have a surface boundary exosphere. And it's a class of atmosphere we actually don't know that much about. So it turns out the moon is actually a really convenient place to go and learn about this really common type of atmosphere. It's also a really good time for us to go and explore the lunar exosphere. Because it's so delicate and thin, it's easily disturbed by things like spacecraft landings. Things have been relatively quiet around the moon in terms of landings for the last few decades, but it's not going to stay that way for long. There's actually a number of countries, a number of private companies that are planning landings to the moon in the upcoming years. So now is a really good time to go and take a look at it while it's still in its sort of pristine, natural state. The second science goal is to look at the dust environment around the room. And if I can get the second graphic. We've actually had questions about the dust environment since even before Apollo. If you look at the image on the left here from the Surveyor 7 mission, it captured something right along the horizon just before sunrise, this strange glow that we think might be due to dust scattering sunlight in the atmosphere. The Apollo astronauts actually saw something similar thing too. If you can see on the right side is a sketch from Apollo 17 astronaut Gene Cernan's notebook, where he saw not just that horizon glow, but also these things he saw streaming high up into the atmosphere, something he called streamers. We think this also might be due to very tiny particles of dust getting lofted tens of kilometers up into the sky. So this is finally an opportunity that we can go and solve this mystery that has been puzzling scientists for almost 50 years. So we're very excited to finally get an opportunity to understand what the dust environment is going to be like around the moon. So we have 3 science instruments, if I can get my last graphic, on our science payload in order to explore these questions. The first is the Lunar Dust Experiment. It is designed and built by the University of Colorado, and it will actually analyze individual dust grains as they approach the spacecraft. The second is a neutral mass spectrometer designed and built by NASA Goddard. It will actually look at the composition of the various molecules in the atmosphere as well as their distribution over the course of a lunar day. The third and final instrument is an ultraviolet spectrometer brought to us by the NASA Ames. And it's not the first spectrometer that we've sent to the moon. We've actually sent a number of spectrometers. Usually, though, when we send a spectrometer, it's looking down at the surface of the moon so that we can understand the mineralogy of the rocks at the surface. This spectrometer will actually look sideways, just above the lunar surface, so that we can go through the atmosphere and analyze what is in the atmosphere and the dust environment. So those are our 3 science payload. There is a 4th payload, as has been mentioned, and I'm going to turn it over to Don to introduce us to that one.
Thank you, Sarah. And I'd also like to thank the Science Mission Directorate and the LADEE mission for giving us a ride to the moon, our technology demonstration, where we're going to use laser communications to demonstrate at least 6 times more data rate from the moon than we can do with a radio system with half the weight and also 25% less power. And my first graphic is up, and if you can see that, it actually gives a good illustration of what the concept of the mission is. You can see the LADEE spacecraft on the left and our instrument at the bottom, which is a little small telescope. And it will basically exchange laser beams between the Earth and the moon to a new type of ground station. So with this system here, we plan to be, or we will be NASA's first high-rate, 2-way laser communications demonstration riding along with LADEE to the moon. The next slide, please. So NASA has a need for faster download speeds for data from space, and it grows every day just like it does for the rest of us at home and also at work. We'd like to be able to send high-resolution images and movies in 3D even from satellites that not only orbit the Earth, but also from probes that'll go to the moon and beyond. So communicating with radio waves has served us well for the last 50 years, but we now have the technology to use light waves to communicate even more data. Light waves are much shorter in wavelength than radio waves, as you can see in the figure, and that allows us to use smaller transmitters and smaller receivers. For example, in the figure, you can see that a typical radio dish is on the left-hand side, and our ground terminal is on the right-hand side. And if you can, on the animation, please play the animation. While we send 6 times more data and use less power, we're actually a bunch smaller, quite a bit smaller, as you can see. So faster bandwidth, smaller size, and less power needed. The next slide, please. So this is an animation of our actual mission concept right here. We have 3 ground stations, and then you can see the LADEE spacecraft, and we've highlighted in bright blue our space terminal. So a beam from the ground, from one of the ground stations, will scan around the moon to where we expect LADEE to be. And when LADEE sees that beam go by, it will send its own signal back down to the ground station so that the 2 systems can lock up and acquire each other. Once the 2 systems are locked and acquired, then we can send tens of megabits of data per second from the Earth up to the moon. And similarly, we can send hundreds of megabits per second from the moon and on LADEE down to the Earth. And so we hope that successfully demonstrating this over and over again during the LADEE mission under all the conditions that you can see in the atmosphere and day and night and moon behind you and such will build the confidence for future NASA missions to use this technology for their communications systems. Finally, I'd like to point out that the MIT Lincoln Laboratory built our flight terminal and also built our primary ground terminal, and we also have partners. NASA's JPL has built a ground station for us in Wrightwood, California. And then finally, the European Space Agency has also built a ground station in Tenerife, Spain. And we're looking forward to collaborating with everyone and LADEE. And at this point, I hand over to Doug Voss, who is our launch manager at NASA's Wallops.
Thank you very much, Don. It's an honor and a privilege to represent Wallops and NASA and be a part of the LADEE team. For the last 5 years, Wallops Flight Facility has been working with NASA Ames and all of the other centers mentioned to deliver LADEE to the moon on its way on an Air Force Minotaur 5. Wallops has been a very busy place in the last couple of years. As you might note, there have been a lot of missions that have been increasing in scope and size at Wallops Flight Facility, and LADEE is launching at a historic time at Wallops. Wallops has been launching missions since 1945, and in all of those flights from Wallops and other places in the world, none of those flights have ever left Earth's orbit. So LADEE is a historic moment, as well as going to the moon. It makes it very exciting for people like me and other people on the team. Wallops is exercising a relationship with the U.S. Air Force that we've been working with for a few years, actually since 2006, to fly Minotaur 1s from Wallops for Air Force DoD missions. So with LADEE, we're putting a NASA mission on top of a Minotaur vehicle, and it's a new Minotaur vehicle that we've never flown from Wallops Flight Facility. So it's a very exciting time for us and the Air Force and the rest of the agency. I have a visualization I'm going to show you and talk to you a little bit about the flight. It's developed by engineers at Wallops Flight Facility, and we use this visualization for engineering and planning. The Minotaur 5 is going to be launching from Virginia Spaceport, Pad 0B. And this 5-stage solid-fuel rocket is going to lift off, as mentioned earlier, 11:27 p.m., Friday, September 6th, and it's going to take off and fly over the Atlantic Ocean. This 5-stage rocket will drop its first 3 stages in the Atlantic Ocean, while NASA systems located at Wallops Flight Facility, nearby North Carolina, Outer Banks, Coquina, and on Bermuda will be tracking the rocket on its flight out. So as the ICBM Peacekeeper stages fall into the ocean, these systems will be relaying data back to Wallops Flight Facility, giving personnel in the Range Control Center and in the Air Force and NASA personnel will be taking that information and observing the flight on the way out. So as the vehicle flies out, it's real important to note that the data coming back from these facilities in the Atlantic Ocean at Bermuda will be used to assess the vehicle and to monitor its performance. It's real important to note also that these stages are ICBM stages that were on Peacekeeper vehicles that were used by the Air Force, so they're highly reliable on the first 3 stages. The 4th and 5th stage are commercial rocket motors that are stacked on them. And right now on the visualization, you see the fairing separation. And that fairing separation exposes the LADEE spacecraft and the new Minotaur 5 5th stage. Upon 4th stage burnout, you'll see that the TDRS system will be used to collect the data as the launch vehicle gets downrange and out of range of tracking assets. So at this point in the flight, the vehicle is in orbit and the stage 4 ignites. And at the stage 4 takes the vehicle up to prepare it for its final phase on the way to insertion. And after stage 4 separates, we enter the stage where the Minotaur 5 5th stage is going to do its work. The first thing we have to do is spin the upper stack together, and the LADEE spacecraft and Minotaur 5 will spin and be spin stabilized before the 5th stage ignites. When the 5th stage ignites, the TDRS data will be transmitted via the TDRS system back to Wallops Flight Facility. And after burnout, the system will despin. We have a yo-yo despin that Orbital Sciences has developed along with the rest of the systems on the 5th stage. This system despins the system so LADEE can separate and then turn on and begin its trip to the moon. So this vehicle is going to be launching at night, so it should be easily visible from a lot of locations on the East Coast. The next visualization you'll see is a graphic of the East Coast of the United States. And go ahead and switch to that graphic, please. And so in this graphic, you'll see that all the way from the coast of South Carolina up to the Maine area and as far west as Pittsburgh, you'll be able to see the vehicle depending on weather conditions. You can actually go online to NASA's website and get this information and figure out which way to look to see LADEE head on its way to the moon. Thank you. And back to Dwayne.
Well, thank you all. Now it's time. We're going to go ahead and transition into the question and answer. We're going to go to the phone lines first, and then, of course, remember, the public that's out there, send your question in to #AskNASA. Join the conversation. It's building and building at LADEE. At NASA LADEE. But if you have a question, again, send it in to #AskNASA. But right now, we're going to go to the phones first, and I believe we have Marcia Smith on the line. Marcia? Well, what I will do, if Marcia's not there, let me go ahead and take and ask NASA question for the panelists.
Is there a mic open?
Okay. I'm hearing Marcia, she's going to be with us. So for the group here, for an Ask NASA question, if LADEE doesn't launch September 6th, what other launch opportunities will there be?
I can answer that. The September 6th opportunity is the first window, and since we're leaving Earth orbit, we have a pretty tight constraints on when we can launch. So we have a window on the 6th, and then we have another 4 nights that we can launch. If we don't get out for some reason, the weather's too bad, then we stand down for a couple of days, and then we can make another attempt for 4 days before the windows close. After that, we have some more windows in October, but we need to get off the ground by the end of October. Otherwise, an eclipse season starts around the moon that has very deep, cold eclipses, and those are eclipses the spacecraft's not designed to survive. So September and October are our primary windows.
Okay, let's see if we can go back to the phone lines here, and I believe we have Alan Boyle. Alan, if you're there, please give your name again and your affiliation.
Okay, all right. This is Alan Boyle with NBC News, and I had a question just about LADEE has had quite a history. I think when the mission was first raised, it was going to support future NASA manned missions to the moon. Now the focus has shifted elsewhere. Do you feel, how did that change the character of the mission? And can you talk a little bit about the long-term goals that are served in terms of exploration by this mission? Thank you.
You want to take a shot at, John? How do you want to do this, John?
Well, the way the question was asked about LADEE being a human mission is not correct. It was never designed as a human mission. It was always a low-cost robotic science mission from the beginning. I'm personally not aware of anything else called LADEE in the agency that was related to humans. So if the question wants to be repeated in any format, go ahead, but LADEE was not designed to be involved with humans.
So I can add to that. I think what the questioner is asking is, at the early times, dust is a very difficult environment to deal with on the moon. It's not like terrestrial dust. Terrestrial dust is like talcum powder. On the moon, it's very rough, and it can actually follow, it's very kind of evil. It follows electric field lines. It works its way in equipment. So one of the questions about dust on the moon is an engineering question. How do you design things so that they can survive the dust environment? And that was the connection to the human efforts at the beginning of LADEE, was not only the scientific question about how elevated dust operates around the moon, transports around the moon, but also information about the dust transport mechanisms for engineering purposes. And the goal of LADEE was to do these measurements before future human activity occurred, which is something Sarah talked about.
I think just to expand on that a little bit, Butler, I think you gave great answers. And another thing that we've learned about the moon from the LCROSS mission is the possibility of water on the moon, and how does it get trapped in these cold traps and other places that we've seen it. And so understanding this tenuous atmosphere and the transport mechanisms of dust and other atmospheric components will tell us a lot about, both the scientific aspects and future lunar exploration aspects. We're exploring all across the solar system, from, just a very rough view. The moon kind of looks like Mercury, and you would never think that Mercury, so close to the sun, would have an atmosphere. But there's some hints that even Mercury, has a tenuous atmosphere from our MESSENGER mission. And so LADEE is part of a much broader scientific exploration of the solar system that we do here in the Science Mission Directorate. But of course, all of our exploration, science or otherwise, is human exploration. I have to remind my kids sometime that scientists are people too, are humans too, especially myself. So this is part of a much broader exploration agenda. And the same question can be asked about larger asteroids. If you look at a Ceres or a Vesta, does Ceres and Vesta in the main asteroid belt, do they have atmospheres? What are the transport properties of dust from collisions? Clearly, the moon is what we see on the moon, the visual surface, is the result of asteroid collisions on the moon. And so in the main asteroid belt, there's, speaking in very long time frames, lots of collisions. And so the same questions are out there. So this is part of the broader scientific exploration.
Thanks, John. We're going to take another call on the phone line, and then we're going to go back to social media. Again, if you have a question, hashtag #AskNASA. Join the conversation at NASA LADEE. On the phone next, Carolyn Chen, New York Times. Carolyn?
Hi, can you hear me?
Yes.
Okay, great. I was wondering if you could explain what the price tag of the mission is and put that into some context with the original goal of the Lunar Quest program to, be less expensive. You've mentioned many times that the new modular design has the possibility of saving money, and I was wondering if you could extend the price tag of this mission and also compare that to previous lunar missions or any other comparable missions to give some context?
Sure. LADEE's price tag's coming in at $280 million for the full life cycle cost of LADEE. And one of the ways we categorize our missions, there's a number of factors, but one of those is cost. And we call them Cat 1, 2, or 3 based on cost and other things. We look at missions that are over $1 billion, between $250 million and $1 billion, or less than $250. And this mission came in at the low end of Cat 2. So it almost made the Cat 1, the lowest cost missions that we have. So it's just over that Cat 1 boundary at $280 million.
Carolyn, did that answer your question?
Yeah, I was wondering if that was could you give some context for that number? Is that what was expected from the outset? How does it compare to, say, the Grail mission or LRO?
I don't have the LRO or Grail numbers. I would guess Grail was Discovery, so that was about $350 million approximately. But I really shouldn't say because I don't know for certain on that. I will say that over the last 10 years, approximately 20% of our missions have been in the lowest cost range, below $250, and 20% have been over $1 billion, and 60% have been in that mid-range.
And Carolyn, you can call my office and we can get you some additional figures to put it in context. We don't want to put those numbers out. We just want to make sure we can get them accurate. So just give me a call on that. So this is what we're going to do, ladies and gentlemen. We're going to go to the real expert on social media who's joining us here today with a Ask NASA question. We're going to switch over to my colleague, Jason Townsend, who's monitoring Ask NASA. Jason?
Hi, we have a question here from Twitter user Daniel Fisher. Could someone on the panel address the hoped-for involvement of amateur astronomers in support of NASA LADEE science goals?
Sure, I can address that. This is Sarah. So yeah, we are very interested in having participation from amateur astronomers around the world. We'd really like to be able to see what's going on the moon. So we're orbiting the moon. We've got LRO looking and stuff, but there are impacts hitting the moon all the time, and we want to know what impact those impacts are having on the atmosphere and dust environment. So we've asked amateur astronomers to actually watch the moon and take a look and see if they see impacts coming in. That requires a certain level of sophistication in your telescope. If you are below that level, we actually have a web app where you can go and actually monitor meteorites coming through on Earth. So if you figure that, as we go through a meteorite storm, certain number of things are hitting the moon, they're also hitting the Earth at roughly the same rates. So we actually are interested in acquiring data about how many things are hitting the Earth at any given time as well. And so there's actually an app. You can find the information for it on the LADEE website. To download the app, it's free. And you can go out at night and count meteors and add that data to our collective knowledge. So anybody can participate in the LADEE mission.
Jason, some more questions.
Indeed. From Twitter user Jim Way, can you explain more about the de-spin procedure? Did you call it a yo-yo?
Yeah, this is Doug Voss from Wallops. Sure, I can answer that question. So the de-spin procedure is important because when the upper stage is spun by the spin rocket motors, the system needs to be despun before separation so that when the LADEE spacecraft separates, there's no forces applied onto it that would cause it to tumble. The despin procedure in this case is using weights that are connected to a cable that are released, and as those weights expand out from the body, the mass, the center of mass moves out from the body, and the inertia is changed, and the whole body slows down and stops eventually. So these types of systems have been used on suborbital vehicles quite a bit by NASA at Wallops, as well as some ELVs before the Minotaur 5. So the concept and the design is actually pretty old. Wallops Flight Facility has been flying sounding rockets in this same way for many, many years. So that's essentially not a new part of the technology, but it is a new element on this upper stage.
And Jason, let's take a couple more questions from Ask NASA, and then we'll go back to the phone lines. Jason?
Sure. Twitter user Ricardo Batalani asks, why do you need to spin up the rocket before stage 5 ignition?
Sure, Doug Voss from Wallops, and I'll take that. The purpose for spin stabilization of the upper stage is actually twofold. When you have a spinning body, Newton's first law is that objects that are in motion tend to stay in motion. So as the body's spinning, any outside disturbances that are applied to it as it flies are actually the body that's spinning, the effect is not as much on the body. The other thing is that while the fifth stage is actually thrusting, the errors that are accumulated are averaged out because the errors from the thrust are pointed in multiple directions at one time, so that error is averaged out. So Orbital Sciences has applied this concept to the upper stage to meet the LADEE insertion accuracy requirements for the mission.
One more?
Okay, from Twitter user Marcia Smith. If LADEE's LaserCom demo works from the moon, will LaserCom work from anywhere in the solar system?
This is Don Cornwall from LLCD. I'll take that. As you go further out from the moon, then you'll need more photons and bigger systems. But at the same time, when you compare what you can do with a laser, because a laser beam can be collimated to be much tighter than a radio wave, you can deliver more energy at a greater distance than you can with a radio wave that might be dispersing. So actually, LaserCom gets more attractive compared to radio as you go further in the solar system. So we hope to use these systems from Mars one day, for example, and there are some research efforts there to look at that.
Okay, we're going to go back to the phone bridge, but again, ladies and gentlemen, keep those questions coming in. Hashtag AskNASA, and continue to join the conversation at NASA LADEE. Back to the phone lines, and I believe we have Irene from Reuters. Irene.
Thanks, Dwayne. I have a couple questions. The first is the $280 million price. Does that include the Minotaur 5 launcher?
Yes, ma'am, it does.
Thanks. And I had another question about the rocket. You know, traditionally, first flights of new vehicles have a kind of spotty track record, and I'm just wondering, from your kind of internal assessments, is Minotaur 5 in this configuration considered a new rocket? And could explain maybe a little bit about what the advantages and disadvantages of picking this as a launch vehicle for LADEE. Thanks.
Sure. This is Doug Voss. I'll answer that question. So the Minotaur 5 vehicle is based on actually a predecessor, Minotaur 4. So the first 4 stages of the vehicle actually have flight history on Air Force missions. The 5th stage is the new element in the mission. It's required to get LADEE into the orbit it needs to get to the moon. So the innovative aspects of this mission are there in the Minotaur 5 5th stage, but individually, none of the technologies are new. So there are a lot of proven concepts folded into a new vehicle. And it is true that this upper stage hasn't flown before. Another good aspect of this vehicle is that it's using existing motors. The first 3 stages, as I mentioned earlier, are peacekeeper motors. So this aspect of the innovation is that we're using retired ICBM assets to fly a science mission, and we're stacking proven 4th and 5th stage motors. The Star 48 is the 4th stage, and the Star 37 is the 5th stage. They are themselves proven motors. So in trade for a lower cost mission, you are, in fact, accepting more risk with a new 5th stage. And that's the decision NASA's made and accepted.
We'll stay on the phone line here. Next caller is Ken Kramer from Universe Today. Ken?
Hi, thanks for taking my question. Good luck for everybody, and I'm really excited to be joining you soon for the launch. I have a couple of questions. One is about the duration of the mission. I guess it's 100 days. I wonder if what is the reason for that, and is it possible to extend it?
This is Butler. I can answer that. The total mission length is 6 months. We take about a month to get to the moon. We take another month to do the commissioning phase of the instruments and the laser comm experiment. And then we drop down. The length of the mission is limited by how much fuel we have. I mentioned that the moon has a very lumpy gravity field. What that means is that you never get truly circular orbits around the moon. And the closer you get to the moon, the more your orbit varies up and down. And so to stay that low above the lunar surface, we expend a lot of fuel. And one of the limitations on how long we can stay there is how much fuel we carry. So it's always an optimization. You can go with a bigger spacecraft, bigger fuel tanks to extend your time above the lunar surface, but then you have to go to a bigger launch vehicle, and it's higher cost, and so it all daisy chains that way. So this mission was designed at 100 days because that's basically the amount of fuel we can carry to get to the moon, drop down into this science orbit, and then and stay there. There's really not a way to extend the mission past that 100 days. We'll go as long as we have fuel available, but ultimately we'll be limited by the fuel exhaustion.
Exciting. For anyone who wants to answer this, maybe even John Grunsfeld, when do you foresee using this on another planetary mission?
Ken, some of your question got cut off. Can you repeat your question again, please?
To follow up on the laser communication system, I'd like to know when that would be. When do you foresee using this on another planetary mission? Thanks.
You know, as I said in my opening remarks, I'm a huge fan of laser comm, and one of the reasons is that as you go further out into the solar system, it's a much more efficient way to get high bandwidth at low power. And so I'm very confident this will be a successful experiment. We'll see in a very short time. So I'm very excited to see and hear the results. And it could be as soon as, you know, our Mars 2020 mission. We've already been having discussions about could you do laser comm on a rover on the surface of Mars, perhaps for a future Mars orbiting spacecraft versus all the way back to Earth or directly back to Earth. But I think this is just the beginning of you know, what will be, you know, replacing some of the radio frequency comm in the future. I think there's no question that as we send humans further out into the solar system, certainly to Mars, that if we want to have, you know, high-def 3D video, we're going to have laser comm sending that information back.
This is Don Cornwell from LLCD. I have a follow-up as well. There is actually a follow-on funded NASA program to do laser communications. It's called the Laser Communications Relay Demonstration. It's going to have a laser comm package on a hosted payload, a commercial spacecraft, and in geosynchronous orbit. And the idea there, in addition to demonstrating more technologies, is to run that from 2 to 5 years to really build confidence in laser comm. We are a short mission here. We hope to demonstrate laser communications, but we really want to build a lot of confidence over time as well.
Okay, one more question for the phone line before we go back to Jason. He has a couple more questions. Thanks. Keep sending those questions in at #AskNASA. On the phone line, Marion Kramer from Space.com. Marion?
Hi, thanks for taking my question. Yeah, I am wondering, is there a particular reason that the LADEE mission was chosen to launch from Wallops? I guess I'm kind of asking why now? And this can be for anybody who'd like to answer.
This is Butler. I can answer that question. As Doug mentioned, the first 3 stages of the Minotaur 5 are reconditioned ICBM motors. And the treaty between the U.S. and Russia only allows a few launch sites for these XICBMs. We can launch out of Kodiak, Alaska, or Vandenberg, California, or Wallops Island, Virginia. Those are the 3 allowed under the treaty. Kodiak, Alaska, and Vandenberg are better for polar Earth orbits, but if we want to get to the moon, we need to launch eastward. And so Wallops Island is the ideal place to launch this launch vehicle to get us to the moon.
Okay, well, we're going to go back to Jason. And Jason, I hear things are stacking up there. What you got for me?
Sure. From Twitter user Emily Lakdawala, are the moon and Mercury's atmosphere similar? And will NASA LADEE help us understand possibly Mercury's exosphere?
Thanks, Emily. That's a great question. This is Sarah. So yeah, we've had the Messenger spacecraft around Mercury for a couple of years now, and we're learning a lot of stuff about Mercury's exosphere. And it turns out it is in many ways similar to the lunar exosphere. It has a lot of the same elements in it. The interesting thing about Mercury is that we don't have any samples of Mercury's surface. So we've actually been learning about what the materials at the surface of Mercury are based on what is getting up into the atmosphere. On the moon, we actually already know what the rocks are at the surface, but being able to compare what's at the surface versus what is in the atmosphere at the moon will actually help us work our way back to Mercury and understand the difference between what we're seeing in the atmosphere and what might be on the ground there. So we're actually going to learn about Mercury even from this lunar mission.
Jason?
Wonderful. Another question from Twitter. This is from user Ryan Thurman. Is there anything the laser communication system could be used for besides space communications that could improve everyday life?
Well, that's an excellent question. Our system is actually based on the same technology that we're all using in our FiOS fiber optic to the home and between the big trunk lines. So in some ways, this is a NASA spin-in of what's going on commercially. We've been able to take advantage of that big commercial base of many and inexpensive components. So the other possibilities are there are commercial companies that talk about using laser communications for satellite networks around the Earth to deliver data around the Earth. So this would help to make them feel more confident with that as well.
One more? Sure.
One more from Twitter user Isaac Young. Once the link is established, is there no communication delay like you'd get with a radio signal?
So that's also an excellent question. Light waves and radio waves both travel at the same speed. They're both the different forms of the same thing, electromagnetic waves. What's different here is that we can pack more bits into any given second, but the time of flight will actually be the same.
Okay, thank you, Jason. And again, keep those calls coming in, and if we can't answer them during this broadcast, we will make sure that we get back to you. And again, we're almost 2 weeks away, and a lot is going on. So back to the phone lines, and I believe we have Marcia Smith back with us. Marcia?
Yes, sorry about the earlier attempt. I think I hit the wrong button. But anyway, I'm curious about the pristineness of the lunar atmosphere. I think Sarah was talking earlier about how spacecraft easily disturb the atmosphere, and so they want to do this experiment now before there are even more launches there. But this one's going to impact the moon, and Grail impacted the moon. So it seems as though these spacecraft are creating a lot of dust themselves. Is that a problem? Are you going to be able to tell what dust was created by Grail versus by comet impacts? Does it matter?
That's it. That's a good question, Marcia. Things impact the moon all the time. So these small spacecraft impacting the moon don't do a lot. I mean, something the size of LADEE hits the moon like once a month. So the moon's not really noticing these things. But when spacecrafts land, they have a lot of fuel that they use as they're landing, and that actually can add a lot of material to the atmosphere. So because the atmosphere is so thin, I mean, it becomes a significant component of the atmosphere when you land something on the moon. So yes, we have impacted into the moon recently, but we have not landed there in quite a while. So a landing like that will disturb the atmosphere for several months, whereas an impact is just part of the usual processes on the moon.
Marcia, did you have a follow-up?
Is this the last best chance to study a more or less pristine lunar atmosphere?
I guess that depends on the rates of when we start landing back on the moon again. But as I said, there are a number of countries and a number of private companies, the Google Lunar X Prize folks, that are intending on landing things on the moon, several things over the next several years. So it seems like it is going to be a busy time for the moon over the next decade or so.
Okay, what we're going to do, we've got a few minutes left, and we're setting the stage here 2 weeks away on the LADEE mission. I'm going to ask the panelists individually, what's going through your mind now? You're 2 weeks away. How do you feel about this mission? And we'll start with you, John.
I'm tremendously excited. We've been working on this for about 7 years. The team's just grown and grown in their ability to pull it all together. There were a number of moments when we weren't sure we'd, be here today for all kinds of reasons. Things happen, but everything has worked out. The team has done an excellent job of building the spacecraft on time. All the testing has gone great. We haven't had any major setbacks. We're here, we're ready, and we all just can't wait to get everything turned on and working.
Butler?
I'm very excited for this mission, and the team is very excited. You've had a lot of people that have been working this, not just for the LADEE phase for the last 5 years, but also before that to prove out this bus design, prototype this bus design. So you've got a lot of people that have spent a lot of sweat equity in this. Once we closed it into the fairing yesterday, we were very excited. It was a little sad too, because that's the last time we'll ever see the spacecraft again, since it won't be coming back from the moon. So you have a lot of people with their fingers crossed, really hoping for the best, and excited to see their baby fly.
Sarah?
This is my first mission. I am really excited about it. And it's been such a joy watching the science team come together. And they've, this is a short mission. They know they have to hit the ground running, and they have been so fantastic in getting themselves prepared and ready to go for this mission. It's been really exciting to watch.
Well, this is NASA's first real opportunity to fly a dedicated laser communication system. And as I kind of alluded to before, on the Earth here, we've been using laser communications and our fiber optics to power our internet and everything else for the last couple of decades. And NASA has really been wanting to take that same technological leap and put it into space. And this is our chance to do that. So we're very excited to get the opportunity.
From the perspective of Wallops and our Air Force partners with the launch vehicle, it's been very exciting to have a NASA spacecraft handed over for the launch vehicle to take onto orbit. Wallops Flight Facility is very excited as NASA's launch range to be sending this spacecraft to the moon. So it's a very exciting time, a very busy time right now in launch preparations, but they've been going very well. And so we're looking forward to a very successful launch and flight operation for LADEE.
Well, ladies and gentlemen, the stage is set. The team is ready. They're excited. John Grunsfeld loves the mission. We all love the mission. And mark your calendar, September 6th, Friday night, 11:27 p.m. Eastern Daylight Time. A night launch, if the weather's right, as you heard, it will be seen not just on the East Coast, but up to Maine, and to the south, West Virginia. A good show. Friday night, mark your date. Again, join us again on www.nasa.gov/LADEE for the latest updates. LADEE, September 6th, a mission of many firsts. We'll see you in Virginia. Thanks for joining us.